Thank you very much. Thank you very much to the organizers for the invitation. Really great to be back in Bonn after 7 years. And to give proper credit first to Carsten. It's the first time I'm trying to follow the Carsten rule for the number of slides, which is the time to speak divided by 2. I did not quite succeed, but let's see how that turns out. I think it's a very good rule. Okay, so I will talk about the Ginzburg Landau equation. I joined work with a PhD student in Bochum, Maria Blum, Christian Löding here in the audience, and Benjamin Dörig from Karlsruhe. So the application that we are having in mind are superconductors. Superconductors are materials that allow to conduct electricity without any electrical resistance. And one of the very crucial properties of superconductors, which makes them so attractive for many applications, is that they expel all magnetic fields, provided that this magnetic field is below a certain critical strength. And when the magnetic field exceeds that critical strength, it is actually possible that the field penetrates the superconductor in isolated points. These isolated points are vortices, and you have basically a current of superconducting charge carriers, superconducting electrons circulating around these vortices. And this is how it looks like in practice, visualized through something called squid microscopy, where you really see that these vortices appear in practice. Okay, and now we would like to be able to simulate these kind of situations. So I will quickly introduce you to the corresponding model. And for that, I will let by omega denote the body that is occupied by the superconducting materials. It could be a block or something like this. So it's just some computational domain. And the superconductor itself is modeled by something called the order parameter. And that order parameter is a complex valued wave function, which is not a physical observable, but you get the physical observable from it. So this is our physical observable by taking the absolute value of u squared. This is a real valued quantity, which is between 0 and 1, and that's actually the density of your superconducting electron pairs. If you measure locally 1, that means you have a perfect superconductor. If it's 0, it means your superconductor is destroyed, nothing is working, and then you have values in between. Okay, but this is basically the quantity that we are interested in. And now let's say you have a certain configuration. So you have an external field that is acting on some superconductor. You know what kind of material you're using. How do we find that order parameter? Well, you will have to minimize an energy. We will have to minimize the energy of the system, the inner energy of the system, which is in this case the so-called Gibbs free energy. And I will not explain all the terms in detail, but the most important thing is that you do not only minimize for that order parameter that you're interested in, but you simultaneously also minimize for magnetic vector potential A. And this magnetic vector potential, again, is not really a physical observable, just like U itself. But once you know that potential, you take the curl of it, and then you get the magnetic field that is in your superconductor. Okay, so the absolute value of u squared, that's the density, and the curl of A is the magnetic field in your superconductor. Okay, once you minimize this, you get u and A, and then you get your physical observables. So for that, as I said, the energy that you have to minimize in this case is this guy here. And let me start with saying what is given. Given is an external magnetic field, something that you apply. If your superconductor is perfectly expelling it, then the inner magnetic field will be 0, but you always have some kind of external magnetic field. And then you have a material parameter. that's this guy here, kappa, which fully describes your superconductor. One parameter is enough. Okay, and how about these terms here? Well, the last one is just a gauge condition. It leads to local uniqueness for your magnetic vector potential. That's why it's typically introduced. The second condition basically says that the curl of A, so A is the potential, the curl of A is the magnetic field in your superconductor, tries to fit the external magnetic field. And this condition ensures that the density of your electron pairs is between 0 and 1. So these are essentially the last two terms, last three terms here in the mean. All right. So this is what we would like to minimize. And of course, first I should say something about the well-posedness of this minimization problem. And this was already studied in a comprehensive work by Chang-Du, who's not here anymore, Max Ginzburg and Janice Peterson, summarized everything in a Science Review article more than 30 years ago. So they studied well-posedness, existence of minimizers, properties, and a lot of things. Okay, and when you heard the talk maybe about superconductors before, then people maybe just start right away with something called the Ginzburg Landau equation. And where is the Ginzburg Landau equation here? It's, well, you get it, sorry, maybe I dropped it here. Since we are looking at a minimization problem, the derivative of the energy in the minimizer should be 0. And if you compute the derivative of your energy, then the corresponding conditions are these two. This is the gradient of the energy in the minimizer is 0, and these two equations here are called the Ginzburg Landau equations. I'll get back to this in a second. I know it's when you see this for the first time, it's overwhelming and very hard to remember. But one thing before I continue, which is important, is that in this review article, it was already proved that once you find a minimizer, then the vector potential is always divergence-free, and it has a vanishing normal trace. Okay, so this is something that you know a priori. Now, I don't want to drag along all these equations here for my talk, because as I said, things will get quite overwhelming in this case. That's why I will make a simplification. But it's important to note that all the results that you see, they essentially still hold if you don't make this simplification. It's for the talk and to hopefully allow you to follow everything in a clearer way. And what is this observation based on? The observation, the simplification is based on the general observation that in practice, if you solve this minimization problem numerically and you look at your minimizers, then the interesting quantity is that order parameter. That's where you will see the vortices, that's where the interesting stuff is going on. Okay, so this is the interesting quantity. Whereas this magnetic potential is quite boring. It's typically some smooth macroscopic function or convex domain. You can prove this is in H2, and you can bound this just depending on the strength of your external magnetic field, which is typically not so strong, independent of the material parameter. So you quickly see that this is not so interesting, and that's why I will assume that the A is given and that we just minimize for U. But as I said, you could also minimize simultaneously for U and A, and essentially the results will still remain the same. Okay, so as a simplified model for this talk, I assume A is given and A is smooth, which is reasonable and consistent with reality. And if I assume that A is given, then the last term here is constant, this curl and this divergence term. So we can just drop it because it's a constant, and the constant will not change the location of a minimizer. So we just drop it and we just minimize for the first term here with respect to u, and that will make things more readable, I think. Okay, so here's a simplified model. Energy, the same one as before, just the last two terms are dropped. We minimize for u, and now what is given is not the external magnetic field, but the vector potential, which is divergence-free and has a vanishing normal trace. Remember, this is what we know already a priori from this review article, and the material parameter. Okay, so now I was motivating the whole thing with all these nice vortices that you saw at the beginning. So where do I see the vortices in this model here? Why do they appear, and what is the crucial quantity in that context? It cannot be A, so it must be this material parameter kappa. And in fact, that's the driving force. So this material parameter correlates in some sense with the temperature. And by that, I do not mean that it's like the temperature itself or scales with the temperature, but if you have a superconductor that has superconducting properties at high temperatures, and high temperatures is like room temperature, that's extremely high for a superconductor, then this kappa will be a large number. So that's what I mean if I say it correlates with the temperature. Okay, so this can be in many settings a large parameter, and what you observe is the following. So if you freeze that vector potential, you keep everything the same, omega is the same, and you just increase kappa, then you will see, the more you increase kappa, the more vortices you will see, and the smaller the diameter of the vortex becomes. So, loosely speaking, if kappa tends to infinity, the number of vortices goes to infinity, and at the same time, the diameter of the vortices goes to 0. But of course, in practice, even at a couple of kappa equal to 100, you will be in tremendous trouble computing the whole thing. But this is essentially what kappa is doing. And the question that I will try to investigate or answer in my talk is the following. So you would like to solve this model. Try to find a minimizer of your energy, and you already know that kappa correlates with these vortices, okay? But you do not know, you cannot look at kappa and say, okay, the kappa is 20, you see, what is that, 8 vortices, and the diameter will be like this. This is, it's not possible, at least to what I know from all the analytical results. You do not know, but maybe you can translate this kappa into a numerical resolution condition. So let's say you give me kappa, I give you a mesh size, and if you use that mesh size and you solve your energy minimization problem in a finite element space with that mesh size, then you should be able to find the physically correct vortex pattern. So that's the question I will try to answer. And the first step, if you want to answer this question, is how do different norms of u actually scale with kappa? That's the first thing that you have to understand. And what you know, of course, that's already what I mentioned, is that in L infinity, u is between 0 and 1, which also tells you in L2 the whole thing is bounded. And then you also see that the gradient of u scales with kappa in L2 here, but you can prove the same thing in LP, any LP norm, so the gradient scales with kappa. Second derivatives scale with kappa squared. Third derivatives, if you can guarantee them, which can be tricky, you can prove that they scale with kappa to the power 3. And probably it continues like that, even though investigating higher regularity for these kind of applications is tricky. Okay, but the most important thing is, for the gradient of u, you can prove it scales with kappa, and the second derivatives, they scale with kappa squared. Okay, so this is an important information, which will help us. And before I show some more results in this direction, something that these kind of scalings directly suggest is to look at errors not in the standard H1 norm, but to introduce a kappa scale norm. This is something that you know maybe from the Helmholtz equation, where this is quite standard, and we use the same thing here. This is the scales with kappa, 1 over kappa makes the two error contributions of the same order. But of course, once you know error estimates in this norm, you can go back and you already can add the scaling again, and you also know how the error behaves in the original H1. Okay, but everything I will present you will be in this weighted norm. Now, back to the question. So, what do we know? Of course, I told you this article is more than 30 years ago, so people must have looked into that problem before. And yes, of course. So let's say exemplarily we have a P1 finite element space. So we try to minimize the energy in that P1 space. We minimize it exactly in H1. What do we know about the error between U and UH? If we assume that we can compare U and UH, which is tricky, I will get back to this, but let's assume we know that we can compare U and UH, then the convergence was actually already answered, again, in that SIAM review article, where they essentially proved that this error goes to 0 with the optimal order. But the tools that they used to prove this were abstract tools, and they did not really allow to trace these kappa dependencies. So it was, well, you get asymptotically, it converges with the order H to 0, as you expect in this case, using P1 finite elements, but it was not clear how that depends on kappa. Okay, so that question is open. And I also should mention that there are lots of works which investigate this question for the time-dependent Ginzburg Landau equation. You can think of it as the corresponding gradient flow to your energy minimization problem. It's not entirely true, but essentially that's a valid simplification. And again, there's lots of analysis done, but nothing that tries to trace this kappa. Okay, so the kappa is how kappa affects the convergence was not investigated. But when you see it, I mean, I showed you how different norms of U scale with kappa. And we know from more than 30 years ago that we expect optimal order convergence. And you might say, okay, but maybe that's not so hard to answer because we can just make some heuristic. And my heuristic would be, okay, let's just, this behaves like the best approximation. In theory, I mean, there is no result, but we know this converges with optimal order. This converges with optimal order, so maybe it roughly behaves like the best approximation. And the best approximation is something that you can easily estimate this is bounded by U minus some interpolation or quasi-interpolation of U, and we know how the different norms of U scale with kappa. And if you do this very simple heuristic, you end up with this estimate here, which says, well, H needs to be smaller than 1 over kappa, and then you're fine. You observe convergence, we resolve the vortices, and everything is nice. But we will be in for a surprise. So, but that's what you expect if you look at the best approximations. All right, and now I will at least sketch a little bit how we proved the actual error estimates for the error between U and UH. But keep this result in mind. Okay, this is, yes? Yeah.
You mentioned at some point existence result for the minimizer, which means is there uniqueness as well?
Next slide, I will get back to this. Thank you. Very good question. Yeah, that's actually one of the crucial issues. Okay, so now if we look into this error, we first of all, of course, have to talk about uniqueness. And uniqueness is an issue. This is not a convex functional, so we cannot expect uniqueness. We can hope for local uniqueness, but also local uniqueness is not possible, and that's very easily seen. So let's say you multiply your function U, whatever it is, could be your minimizer, with a complex number that is 1 in modulus, then it's easily seen that this will not change the value of your energy, remains the same. Okay, so you essentially have infinitely many minimizers, and worse, in every neighborhood of a minimizer, you will find infinitely many more minimizers. Physically, this is not an issue because all these minimizers here, they share the same density, and the density is the physically important quantity. So physically, it's not an issue, but practically, you have to be aware of this and you have to take care of this. Okay, so we don't have local uniqueness in the classical sense. What else do we know? What can we use in the error analysis? Well, we can use the first and second order conditions for minimizers. So the first one is something that you already saw. The Ginzburg Landau equation, now in the simplified setting. So since we have a minimizer, the derivative of the energy should be 0, this condition. And we can also compute the second derivative of the energy. You don't have to remember it. Okay? This is what you get. And since we have a minimizer, we know that the spectrum of that second derivative cannot be negative. And ideally, we would hope that the spectrum of this operator is positive, and we can exploit that and make a bilinear form based on that operator, which we can exploit in the error analysis. But yeah, we already know that it must be a singular operator because we don't have local uniqueness. So there must be an eigenfunction to the eigenvalue 0. And I could show you the calculation to see what eigenfunction it is, but I think it's best explained with a simple picture. Let's say this is one minimizer, and these are all the other minimizers that you get by multiplying u with a complex number that is 1 in modulus. So all points on the circle line are minimizers. Energy does not change as long as you follow that circle line. And if the energy is constant on the circle line, it means the first and the second derivative of the energy on the circle line must be 0. So we just have to find out what is the direction here that we follow the circle line, which is tangential to that point, which is IU or minus IU. So these are the bad directions, and if we would apply the second derivative to the direction IU, we would end up with 0, which means this is a singular direction. And you can also easily verify this by a simple calculation. Once you plug it in, you will see that this is true. Okay, so 0 is an eigenvalue, but if we have local uniqueness, aside from these so-called Gauss transforms, then all the eigenvalues, the other eigenvalues are positive, which means that we can consider the orthogonal complement of this eigenfunction and just do the analysis on that orthogonal complement. And something I should mention here, orthogonality is measured not with respect to the usual complex L2 inner product, but the real part of the L2 inner product. And if you've seen this before, then you know where this pops up, but it's very natural. It's a very natural inner product in this context, and the reason is that the energy that you want to minimize is a real valued energy. So if you want your energy to be Frichet differentiable, it must be a real Frichet derivative. And that's why you have to equip your Hilbert spaces, which contain complex valued functions, but you have to equip them with a real inner product, and this is the correct inner product in this case. So in a nutshell, why we need this. Okay, but now, as I said, on the orthogonal complement, if we have local uniqueness, all the other eigenvalues are positive, which means we have im sub stability for that operator. With some im sub constant, which depends in an unknown way on kappa. There is a kappa entering here. We don't know in what way it enters, but there is an im sub constant, and it depends on kappa. When you see this, then the first thing that is very tempting is to now build the error analysis around this operator here and introduce the Ritz projection with respect to the corresponding bilinear form, which is, however, not a good idea, because the moment then you estimate the error between you and the Ritz projection with respect to this operator, will directly insert this im sub constant. Since we do not know how that depends on kappa, this is not a good idea. So we will work around this. Then something else, if we want to exploit this bilinear form, we have to work in that space, the orthogonal complement of IU. How does this relate to UH? So what we need to use this quantity here for UH itself is that UH, your discrete minimizer, must be orthogonal to IU. And practically, this is not hard to achieve. You can actually just multiply it. There exists a constant, which is 1 in modulus. You multiply UH with that constant to achieve this property. And that essentially means that UH and U are in the same phase. So they are aligned. Remember, we don't have uniqueness. We can multiply them with the complex number. But if this is fulfilled, then essentially their phases are aligned, and we can compare them in a proper way. So that's why this condition basically means they're in the same phase. We can compare UH and U, and you easily achieve this by multiplication with a complex number. So now back to this part here. As I said, we don't want to directly work with the second derivative to introduce a Ritz projection. So what we did instead was we dropped the nonlinear contributions from that second derivative and only looked at the linear part, which is the first part. This is what appears in that second derivative of the energy. Drop the nonlinear contributions, but the first part alone is perhaps singular. We don't know. We cannot really say if this is a product or whatever. So we have to stabilize it with some sufficiently large L2 contribution. And if you do this, you end up with this bilinear form here. And there you can actually prove that this is coercive and continuous with constants independent of kappa. So this is perfect for introducing the Ritz projection, and this is the usual thing. Okay, now everything is done on that orthogonal complement instead of the full space. But still, if you do that, you can prove that the error between any function v orthogonal to IU and the Ritz projection is as good as the best approximation. And two things to note here. This is not a fully trivial result, because here we project into the intersection of the finite element space and that complement, whereas here it's gone. And that actually, in order to take that step, we required the condition that H should be smaller than 1 over kappa. Which is fine, because we already know this is anyway what we need for the best approximation, but just to note that this is behind this. Okay, and now we have everything together to give you a glimpse of the basic proof idea in one slide. So this is the core strategy. And I show you the core strategy because then you will see what's going on, why something is breaking. Okay, so we have U and UH in the same phase. We first split it up into U minus the Ritz projection, which is nice, it behaves like the best approximation, wonderful, plus Ritz projection minus the actual discrete minimum. This is in the same phase as U, so we can apply the im sub stability to that latter term here, which introduces the second derivative of the energy. Now, all that we have to do is, we have to estimate this latter term here and prove that it is of higher order. If so, then the first term is dominating, and then we would get what we expect. So for that, we insert and subtract u one more time, and we get two different contributions which are small for different reasons. For the first term, we exploit that this Ritz projection was defined based on the linear part of that second derivative, which makes the higher order contributions, the gradient contributions, cancel out. And all that is left, actually, because of this very particular construction here, is a higher order, so higher order in terms of error, contribution of the error. U minus the Ritz projection in L2. Of course, this is a lot of technical details. Here is the hard part to prove this, but this is what you get. Good. And in the same way, for the latter term, you exploit the Ginzburg Landau equation, so the derivative of the energy in U is 0 and the derivative of the energy in UH is 0 on the finite element space. And again, it's very technical, but by exploiting this, you again get the higher order contributions to be cancelled out, higher order gradient, I mean, and you're left with errors that are neglectable compared to what you actually want to estimate.
Could you remind me of the triple bond non-kappa?
Yeah, sorry, I did not introduce that. That's simply this H1 kappa inner product divided by the, it's induced norm.
Is it due to H1 kappa? Or what is it?
It's divided by the H1 kappa. So,
just to do it now.
Yeah, exactly, just to do it now.
And you don't write this as H1 kappa star or something, or -1?
Yeah, I should have. I just noticed I forgot to introduce it. I could have made this in a more compact way. Yeah, thank you. Okay, but the main thing is you can basically play an absorption argument once you have this and hide certain terms in the left-hand side, and the dominating term will be the one that remains here. But at the same time, we always have this im sub constant here, in front of this term here. And if you play the absorption argument and you see what is left at the end, then you will see that this is the actual error estimate. So your error between U and UH behaves as the best approximation, but by a constant which depends on kappa and the im sub constant. And here you see it is not sufficient that H compensates for 1 over kappa, kappa, but it also has to compensate the size of your im sub constant. And if I write it down for the P1 finite element case, then here maybe it's more clear. You essentially get asymptotically the expected rate, kappa times H, but you have this additional term which shows, well, in order to get small errors, your H has to work harder. And the first thing when we saw this was, okay, maybe we were not successful in doing an optimal error analysis, right? Maybe we missed something at some point, and this is really just an artifact of the analysis. But you actually quickly see this in experiments. So some experiments, again, model problem, the same situation I was showing you before. A is given. We use the gradient flow to find the minimizers. And long story short, here is what you see. Okay, H1 errors, L2 errors. The dotted lines, hard to see, they are the best approximations. And what you see is, directly in the regime, H is smaller than 1 over kappa, the best approximations, they converge, just like you expected. They go down following the asymptotic rate that you expect. Whereas the real minimizers, they have a clear pre-asymptotic regime where the error is not going down. It's stagnating, it remains constant, and only eventually, when something is resolved, probably this condition, it goes down and you see the expected asymptotic convergence where your errors match the errors of the best approximation. And you see this equally for your H1 arrows and for your L2 arrows. It's in both cases. And of course, we already have seen the explanation from the theorem, but we tried to understand it a little bit better and also had a look at the energy. So the energy of the minimizer compared to the energy of the best approximation. And what you observe is the energy of the best approximation, so of the good guys, is too high. It's much higher than the energy of the actual minimizers. And that's why they are not found. So their energy is simply too high in these spaces. Okay, so, one more thing. We also, of course, try to figure out a bit how that subconstant actually scales with kappa. So we computed the eigenvalues of the second derivative, and what we saw was, to be optimistic, the subconstant scales with kappa, but sometimes we even saw something like kappa to the power 2 or kappa to the power 3. It's not clear yet, but optimistic, in an optimistic estimate, I would say it at least scales with kappa, so the inverse is 1 over kappa, and that means that the effective resolution condition that you need is not h smaller than 1 over kappa, but h smaller than 1 over kappa squared, which is of course a significantly stronger condition than what you would expect when looking at the best approximation. Okay, and with this I want to spend my final few minutes to show you how things can be reduced, relaxed by using a multiscale approach. So for that, I use a construction in the spirit of the LOD or also in the spirit of Gamblets, which works in the following way. So we take, again, this inner product, no, not inner product, I'm wrong, this bilinear form that we have seen before, which is the linear part of the second derivative of the energy. That induces some operator, and our multiscale space now is the inverse of that operator applied to finite element functions. This is essentially the LOD construction, maybe not in a way as you have seen it before, but you can prove that this is essentially the same. Okay, so this is the space, but remember before we had to stabilize it, and I was telling you we have to stabilize it because it's maybe singular, we don't know, and this did not change, but you can actually prove that this is still well posed, provided that h is smaller than 1 over kappa. So even though it might not have an inverse for all right-hand sides, this is still well posed, provided that this resolution condition is fulfilled. Okay, so we can work with that space. And the idea behind this is to incorporate this critical term of the energy and to hope that the corresponding approximations become energetically more favorable in that space. Why can we hope for better approximations? Again, just in a nutshell, let's say you use this bilinear form here, you define your space like this, and now you say you have some function set which fulfills an equation of this form. It does not have to be well posed, right? You don't need to have a unique solution, or you don't have to have a solution for each individual right-hand side. All you know, there is a set which fulfills an equation like this with this bilinear form up here. And if you follow the classical LOD arguments, then you can actually prove that the error between the set and the best approximation in that multiscale space here behaves independent of the regularity of this guy, like h times kappa times something that might improve the situation depending on the regularity of your right-hand side f. And here you have the standard finite element space. Okay, so if f is in H2, you might be able to squeeze out 2 more h's here. And that gives you an h to the power 3 instead of just a simple H without exploiting any higher regularity. And the way how we use this result is Z is our U, and we use the Ginzburg Landau equation to phrase it in a form like that. In this case, F will depend on U in a polynomial way, not on the gradient, but U to the power 3 or something like this. But that's fine because we know U is an H2. So we have this function depending on U minus the best approximation. It will allow us to squeeze out 2 more H's, but the price is U in the H2 norm, which we know scales like kappa squared. So we gain 2 more H's, but we also have to pay with 2 more kappas. But if you do that and you follow the arguments, then at the end you will end up with an estimate like this. Same irregularity requirements as before, same dimension as the P1 finite element space, and what you see here now is we still get an additional term. It's not gone, but the resolution condition is much more relaxed. Before, we had to fully compensate for the size of the subconstant. Now it's just a quarter, 1 over a quarter, which is of course a tremendous reduction of the necessary resolution. And here is how that looks like in the experiments. You still see, so as before, dotted lines are the best approximations, which again converge right away. Solid lines are the actual minimizers now in the multiscale space, and you still see a pre-asymptotic regime, which is consistent. I mean, we could not remove it. It's still here, but it's much shorter, and very quickly we enter the same approximation order as for the best approximations. At the end, things are flattening out, but the reason is simply we could not get a more accurate reference solution. That's the reason. Otherwise, we really observe what we want to observe. And I think it gets even clearer if you have a visual comparison of the actual minimizers. So same mesh size, P1 finite elements, compared to the multiscale space. What you see is, at the beginning, your standard finite element approximations, they don't get any meaningful approximations. Only at this mesh resolution you start to see the correct vortex pattern. Whereas in the multiscale space, even for this mesh size, I think this is a 9-dimensional space, you already see the vortex pattern. The error might still be large if you measure it, but you still see the number of vortices is correct. You essentially can see where they will form, even though this is a super low dimensional space. And then, of course, you go to the next final mesh, you almost have, in the I norm, your correct vortex pattern. So it really helps for these kind of situations. Okay, that was it. So these are the 3 relevant works. This is the first work where we discovered this pre-asymptotic effect. We did it for standard finite elements, and we discovered that there is something that went unnoticed so far. Then the work where we did it in the multiscale spaces, so the results that you saw the last, and then where we, now in preparation, almost done, any week it should be on archive, where we prove that you can include A in the minimization problem and nothing will change. So it does not matter if you say A is given and you look for U, or if you simultaneously minimize for U and A, the results are the same. Okay. Thank you.